so in the previous video, at the last part, we learned about how to convert the carboxylic acid to its derivatives. Okay, I just want to stress that this carboxylic acid and derivatives, they undergo the same main type of reaction, which is nucleophilic acyl sub or condensation. Okay, so what do I mean by the word acyl? I just want to stress that the word acyl is referring to anything with C double bond OX, okay, where X is Cl, OH, OR, or N. I want to stress that N is not always NH2, but it could be NR prime. Okay, so this is what it means. Okay, in fact, this one may not be NH2. I'm going to erase this. Okay, so I just want to stress that for an amide, right? Okay, you have a C double bond O, N. That's all. Because nitrogen has 3 bonds when it's got no charge, so nitrogen has 3 bonds. So these two groups, right, could be H, that's the simplest amide, primary amide. Okay, or you can replace with R, secondary amide, or you can replace with another R, the H with another R, then we can call it a tertiary amide. It doesn't matter, okay, how many R groups and hydrogen there are bonded to the N. Once I have a C double bond ON, this is straight away an amide already. Okay? Okay, so the question is, why do they undergo nucleophilic acyl sub? Okay, the fact that they attract nucleophiles tells me that they all have a delta plus carbon. Okay, and this delta plus carbon is going to attract nucleophile. So they will be attracting nucleophile. So as I mentioned, you always put yourself in the shoes of the functional group. Ask yourself, if you are that functional group, what do you attract? If you attract nucleophile, then that functional group undergoes nucleophilic reaction. And why substitution? Because the OH, this group I'm circling now, they can be substituted with another nucleophile. Okay, and the acyl here, as I mentioned, is referring to RCOX, where X is a non-carbon or hydrogen. So X is a Cl for acyl chloride, Cl for acyl chloride, OH of carboxylic acid, OR prime for ester, and N to two other groups is for amides. So the word acyl is to differentiate this type of reaction from the halogenal alkanes, which is truly nucleophilic sub. Right? This acyl is to distinguish from the nucleophilic substitution of halogenal alkanes. Okay, so another name that we accept in place of nucleophilic acyl substitution that carboxylic acids and derivatives undergo is condensation. So let's look at some concrete examples. Okay, in fact, you realize that all 4 of them, they attract a common nucleophile. What is it? It is water. Okay, so I'm going to look at the most reactive carboxylic acid and derivative, which is acyl chloride. Acyl chloride is the most reactive. So we're going to look at what are the reactions that it undergoes. Okay, so now let's take a look at what are the types of nucleophilic acyl sub that acyl chlorides undergo. These are the most reactive among the 4 of them. Okay, so with water, acyl chloride can react to give us carboxylic acid and HCl. Okay, instead of writing it this way, I'm going to write it this way. And can you see that it is actually a condensation because my HCl comes out here. And then the OH will substitute the Cl here. Therefore, the Cl is substituted with the OH. Therefore, it's a nucleophilic acyl substitution. Right? The Cl is substituted with OH, right? Nucleophilic acyl substitution. Okay, this reaction occurs readily at RTP, and why I choose to write it dissociated is because HCl aqueous state is dissociated because HCl is a strong acid. In fact, I just want to point out that the test, do you recall what is the test for acyl chloride? Do you recall what is it? If you have forgotten, please go back and review your deductive handout, which is extremely important. Okay, so in the deductive handout, it highlights a lot of reactions that you need to know for deduction. So you need to internalize your entire organic chem. So if you've forgotten, please go back and understand and internalize and memorize your deductive handout. So for acyl chloride, we add silver nitrate aqueous. The aqueous provides the water, which will react with the acyl chloride to form H plus Cl minus aqueous, and the Cl minus aqueous is the one that react with Ag plus to give us the silver chloride. So we see an immediate white PBT at RTP, no heat is required. Acyl chloride is very reactive. All these reactions occur at RTP. Okay, so if I see a white PBT straight away with silver nitrate aqueous, I know that acyl chloride is present. Okay, next, what about with an alcohol? Okay, so let me write it this way. And can you see there is again condensation? HCl comes out, and then the OR prime will substitute the Cl. Again, nucleophilic acyl substitution. Cl is substituted with this. What about ammonia? Okay, I'm going to again write it this way, so it's easier for you to see. HCl comes out as a condensation. Condensation means I lose a small molecule from between two compounds. Okay, from between two compounds, I lose a small molecule, HCl coming out, condensation. And then the NH2 will substitute the Cl. Again, it is a nucleophilic acyl substitution. The Cl is substituted with NH2. Okay, so these three reactions highlights the nucleophilic acyl sub or condensation reactions of acyl chloride. You can see that in all these three cases, the Cl is substituted with another group. That's why it's substitution. Okay, and this is actually a nucleophile. Okay, the water is actually a nucleophile, the lone pair that attack the delta plus carbon. Okay, I'm not going to talk about the mechanism in this slide here. Okay, so I'm just going to talk very quickly about how about the esters and amides very quickly now. Okay, what about the esters? Okay, for the esters, they undergo these reactions, okay, with water as well. So with H2O, you can do a hydrolysis of an ester, okay, and what will happen is that this will come out, so you're going to get carboxylic acid and the ester, and the alcohol. Okay, so it's again condensation. This one will come out here. So I just want to highlight that all four undergo hydrolysis. Oh, sorry, except carboxylic acid. What I mean is the derivatives all undergo hydrolysis. So what is happening is that again, you can see the pattern is very similar. I take out the H and RO prime. This will come out as a condensation. A small molecule will come out of alcohol, and then the OH will substitute the OR prime. Okay, so it's quite similar to the acyl chloride hydrolysis, except that for acyl chloride, right, the hydrolysis occurs at RTP, but for ester, you cannot just use water at RTP, nothing is going to happen. So you need to heat. First of all, it's harder to hydrolyze the ester, and can you just use water heat? No. Okay, we will need to use either some acid catalyst, heat, sulfuric acid aqueous heat to hydrolyze the ester, or we will need to use sodium hydroxide aqueous heat. So what's the difference between alkaline and acidic hydrolysis of ester? Okay, so if you look at this, right, okay, I rewrite the same thing again. But however, if I were to do an alkaline hydrolysis, sodium hydroxide aqueous heat, then instead of getting carboxylic acid, because it's alkaline medium, I'm going to get COO minus Na plus and the alcohol. Alcohols are neutral. So I'm just going to get these products. Okay, so similarly, what about for amide? Let's look at the last case. So the common reaction to these three is hydrolysis. Okay, but by now you should know that acyl chloride really reacts very readily. Okay, with all the nucleophiles, and even with hydrolysis, it's at RTP. HCl just come off. RTP. But for ester to be hydrolyzed, you need either acid or sodium hydroxide aqueous heat. You need either acid or base catalysis. Similarly, for an amide, it's the same thing. You cannot just use water heat because it's harder to hydrolyze the amide. So you either need to use the acid catalyst or base catalyst. So if I were to use acidic medium, sulfuric acid aqueous heat, then I'm still going to get the carboxylic acid, but because ammonia is basic, I'm going to get NH4+. Okay? This N has 4 bonds, NH4+. Okay, so ammonia is, ammonia is basic, so you accepted the H+. So what you do is that for hydrolysis of amide, you just hydrolyze it, okay? The OH comes to this C, the H comes to this N. You get the hydrolysis product first. without the H plus or H minus, then you decide the medium, H plus, because you know the medium is H plus, if you choose that. Then you see which of the products will react with the H plus. Carboxylic acid, being an acid, will not react with the H plus. Okay, ammonia is being basic, will react with the H plus. Okay, so you can finish off the alkaline medium case. Okay, so for the hydrolysis of the amide, okay, in alkaline medium, you break this bond, add the OH here and the H here, hydrolysis. Hydrolysis is using water to break a bond, so you break this bond, OH will come here, H will come here. So I again get ammonia and carboxylic acid. But decide, because in alkaline medium, the products who will react with the OH minus, it is the acidic carboxylic acid. So I'm going to get these products here. Okay? So all the acid derivatives undergo hydrolysis, but acyl chloride is straight away at RTP with just water alone. But for amide and ester, you need to heat, and you need to use either H2SO4 equals heat or NaOH equals heat. You can also replace H2SO4 equals heat with HCl equals heat. Okay, so I've written over here what we have just summarized. Esters undergo hydrolysis in either acid catalyst medium or a base medium. Just have the word aqueous because using water to break a bond. Then the acid H2SO4 or HCl equals heat. Then I'm going to get this carboxylic acid and alcohol in acidic hydrolysis. In base hydrolysis, I'm going to get the salt of the carboxylic acid and alcohol. Remember, alcohol is neutral. Okay, so over here on the right, I summarize what we have just discussed. For amides, it undergoes hydrolysis. Again, either acid or base catalysis. And then in acidic hydrolysis, I'm going to get the carboxylic acid. Amide is hydrolyzed to give us carboxylic acid and NH4+. In the alkaline hydrolysis, the amide is hydrolyzed to give us carboxylic acid, the salt of the carboxylic acid, and the ammonia. Okay, and we will be able to get ammonia gas and test for moist red litmus paper turns blue if you want to test for this amide. So similarly, if I have a distinguishing test, I want to distinguish between two esters, I got to do a hydrolysis first and then test for the alcohol products. Okay, either through oxidation, okay, or if one alcohol can be oxidized, the other one cannot, for example, tertiary alcohol, or it could be one alcohol can undergo trial form, the other one cannot. Oh, sorry, I realized I'm missing an arrow here. Okay, acyl chloride can easily react with alcohol at RTP to give us the ester. Okay, but I just want to stress that you go back and revise on how to form an ester with your phenol. Okay, you have to use you have to use acyl chloride, and you have to convert the phenol to phenoxide. Okay, go back and review that reaction on your own. Okay, the last reaction I want to talk about is reduction of esters and amide. Okay, so amides can be reduced using lithium aluminum hydride, represented by this green part. Okay, I will just finish up with the last reaction, which is reduction of ester and amide. Okay, so it's very difficult to reduce amide and esters. So let's look at reduction of amide first. Reduction of amide is more straightforward. You simply just reduce the CO group of amide to CH2. You can see CO group is reduced to CH2. So an amide is reduced to an amine. And this reaction can only occur with the strongest reducing agent, lithium aluminum hydride and dry ether, because it's very difficult to reduce an amide. Okay, for an ester reduction, also very difficult to achieve. So I'll also need to use lithium aluminum hydride and dry ether. But the special thing about the reduction of ester is that I'm going to get two alcohols. So how do I get the pattern? I want you to imagine that the ester breaks up into RCOOH, R'OH. It looks like a hydrolysis, but the reaction is not really a hydrolysis, it's a reduction. I want to stress that it's a reduction. But for the ease of getting the products, I just want you to imagine it breaks up into these two fragments like in hydrolysis. Not truly, I'm not saying hydrolysis occurs, it's not. Okay, but you break it up into these two fragments, the carboxylic acid and alcohol, and then you reduce the carboxylic acid to this one. Okay, so that's how I get the two products. Because if you recall, a carboxylic acid can also be reduced to a primary alcohol using lithium aluminum hydride. So if carboxylic acid is reduced to by lithium aluminum hydride and dry ether to the primary alcohol, so this is what happens in this case. So for reduction of ester, I'm just going to get these two products here. Okay, so for reduction of ester, you're just going to get these two alcohols here. Okay, I just want to stress that this is the aliphatic flow scheme. The aromatics flow scheme is not here. You got to go and write on your own and draw it on your own. Okay, and draw on a big mahjong paper or A3 size paper to connect all the functional groups together. Okay, don't neglect organic chemistry.